Um, so my name is Amber Du, and I will be teaching the R workshop today and tomorrow. I intend to make this session as interactive as possible. I am only here to share my experience with R and programming. So if you have any questions, or if you have any answers to other people's questions, please feel free to unmute yourself and interrupt me. If you're not comfortable unmute yourself during the recording, you can also put your questions or your answers into the chat box. I will make sure to keep track of it. Yeah, do you have any questions? If not, I'm gonna continue. So we're all here to support you, so please ask me anything and I'll do my best to help. So for the materials for today, I sent an announcement on Slack earlier this morning. Maybe you don't have a time to take a look at it yet, so I'm gonna send the link to the materials here in the chat box. So all of the materials for the R workshop today and tomorrow will be available on GitHub. I will also update any changes after today and tomorrow's session. So has anyone working with GitHub before? If you have, please put maybe type 1 in the chat box. If you haven't, just put 0. Okay, cool. I see someone has worked with it before. Oh, 0.5 pay. Okay, I think almost everyone has some previous experience with GitHub, which is cool. So in order to download every materials for SICSS-Howard Mathematica, there's a few options. So if you have downloaded GitHub before, you can just try to click on code and open with GitHub desktop. If you do not have a GitHub desktop, you can also try to download zip and then unzip the folder. After that, you can just open RStudio to access all the materials. It's basically the same. So this is the GitHub grapple. And for the R workshop today and tomorrow, I believe today we will be meeting from 2:30 to 5:30 Eastern time. And tomorrow we will be meeting about 30 minutes early from 2 to 5 Eastern time for tomorrow. So these materials are for SICSS-Howard Mathematica 2023. They're inspired and borrowed from J. John Kim's version from SICSS-Howard Mathematica 2021. So if you want, you can also take a look at the previous version. Below, I have attached a few references and also a few cheat sheets that I find helpful when working with R. You can just click on the link and take a look at it. So basically for today, the schedule is to take a look at how R and RStudio works. Then we're gonna get a big picture of programming. So the two building blocks of R, the objects and functions. And then we will be talking about importing and exporting files in R. And then at the very end, we will be playing with R data types. So vectors, data frames, lists, factors. And for tomorrow, the schedule is to take a look at the master framework, the tidyverse, and learn about tidy principles. Then we're also gonna run some statistical models and plot data in R using ggplot2. If we have time, we will also go over some machine learning packages in R, like how you work with training, testing, validation data set, and how you build a tree, how you do KNN, and those stuff. So for the schedules, if you have any particular topics you would like to go over, You can send me a Slack message or email me, and I'll try to cover it today or tomorrow. If not, I can also upload a notebook to the GitHub, so you can have all of the tools you need for doing the research analysis. And for the workshop goals, I think most of you have filled out the skills survey before the institute. I think some of you has learned R before, some of you has used it for a class project or use it for research for your dissertation. Some of you has trained models with R before. So the goal for today and tomorrow's R workshop is to, for the beginners, we're gonna teach you all the tools you need for doing data analysis in R. And for the people who have worked with R before, we'll try to refresh your memory about some data types, functions in R, and also trying to cover some machine learning packages in R, so you have the tools you need. Great, so those are the goals and schedule for today and tomorrow. Let's talk about the setup in R. So has everyone downloaded R and R Studio on their laptop? You can type in 1 if you have R and R Studio, so we can maybe go quicker. Okay. I think almost everyone has downloaded R Studio, so I'm gonna just quickly go over that so we can move into the other content for today. Yeah. So what is R and what is R Studio? R is basically the programming language for studio computing and graphics. You can consider it as an environment where the techniques are implemented. And some exciting thing about R is that it can be further extended via different packages. So, but R Studio is more like an integrated development environment for R. It allows you to view the data set, view the graphs, and do data manipulations in a more interactive way. So since everyone has already downloaded R and R Studio, we will skip the session about installation. So basically, there are 4 panels in the R. You can, if you want, you can click on preference and then take a look at the different layout. Personally, I tend to put source on the left-hand side and then console on the right-hand side, but it depends on what you feel comfortable about. Also, you can move the environment and the files package section here. You can just choose where you want to put those. So for the okay, yeah. So for the source panel, this is usually where you put a lot of your code. You can organize your code in R Markdown or R script file. And then when you exit the code, these will be reflected in the console. So you can type directly in the console when you want to do some analysis. One thing about it is that it will not be saved during the session. So if you want to save your code, it's more safer to just choose like different types of documents. For example, with R script or R Markdown, you can put all of your code and organize it. But here for the console, it is good for general testing. For example, if you have write a function, it is and you just want to test whether it works or not, you can just use this panel to do it, so you don't save too many variables. And then there are other two panels over here. So this is the environment panel, and it saves all of the variables that we defined in the current session. We will talk about it later about importing data set and the packages in R that are installed. Here we also have the file system, packages, help, VRAM presentation. I think the tab we are going to use the most for today and tomorrow is this package and also help tab. This allows you to get some help with the functions in R. For example, if you just type in $min, it will return the help page for the main function. In the console, in this tab, the console terminal render and background jobs. Another pretty helpful tool is the terminal tab. So this is basically the command line tool for you to do some computation, but also organize the files. There are some advantages of using the command line tool versus like writing a script in R or Python. For example, it is easier to navigate. And also some of the computations are faster if you do it in the command line tool, especially when you have like huge data set. This can be helpful. So we're gonna go over some of the command here. For example, if I type ls, it basically returns all of the files and the current directory. So right now I'm in the directory SICSS-2023, but I also, I'm gonna go back to the root directory. So if you type cd, that basically means you wanna go to some directory. Usually if you put if you want to go to desktop, you can put des or d and then hit tab. It will autofill the rest of the folder's name. So I think my folder is this one for SICSS-2023. And while I'm in this folder, we do ls to take a look at all of the files that are currently in this folder. Then we can also make a new directory via this command. Maybe we'll do like test. This means we have created a new folder called test under the current directory. So if you don't remember what is the current directory, you can always put pwd to take a look at what current directory you are at. So right now we just created a new test folder under this directory. Another thing about command line tool that is pretty fast is that here it is easy to create document, a text file. For example, now we're at this test folder that we just created. So we cd test, and then we are here under the test folder. The folder name is shown here. So echo is the command line tool that you use to print something. So if we see echo hello world, it basically prints hello world. It's like the print function in R, but I also can create hello world in a text file. So here, with this line, we just created a new file under the test folder. This is the test.txt file we just created using this line. And if we want to take a look at the content in the test.txt file that we just created, we can use more test.txt. So remember, you don't really need to type in the full name. Sometimes if you put T and then you hit tab, it will autofill. So for the more function, it gives you a way to take a look at this file. So because the file is like really short, only with one line, this is the end. But if you have like a really large file, you can use more text.txt to avoid loading all of the text at once. So that may slow down your computer. If you want to end the current session of viewing what is in the task.txt file, you can put Q so that brings you back to the command line. Also, if you just want to view the first few lines, you can also use had. But because this file is pretty short, it only returns the first line. I believe if you use had -n 1 or like the number of lines you want to view. For example, if you have a large file, you can use 10 to look at the first 10 files in test.txt file. If you want to view the last few lines, you can also use tail -n10 to look at the last 10 lines in the test.txt file. So we're not going to execute that because we only have one line here. These are a few command line tools that might be helpful. Now we're going to talk about the console panel, the source panel over here. So there are a few options when you want to work in R about how you want to organize your files and your code. For example, you can use RScript. So RScript is basically a file containing all of your code. It expects you to put in the code directly. For example, print hello world. It does not expect like some of the text. Maybe if you want to take some notes, like go over the R command line tools, if you just put something over here, it expects to execute this line. So if you just want to take a note, you can comment it out so that this line will not be executed when you run the whole file. We can also put something like a really simple calculation over here. If you want to execute this, just put Control and Enter, then it will be executed in the console panel. Similar to this one, if you put Control Enter, it will just execute the code and also print out the result on the right-hand side, basically the console panel. Another file that is pretty helpful is also the R Markdown file. So personally, I feel like R Markdown is a great way when you do teaching and also demonstration because you can put both text and code in the same file. And basically, it's like a LaTeX when you do the text. I'm gonna create this one just for demonstration. So you can put the title over here and then the author, date, output file. So a few things about R Markdown. This is the part where the code comes in. So we call it the chunk. You always need to put here. So it is defined via this. Sometimes you can put different arguments over here. For example, echo equals false basically means it will not print out any results. For example, if you put 1 + 1 over here and then you execute it, you don't want, when you need the file, you don't want other people to see the result. So you can put echo equals false. Sometimes if you don't want to execute the code, you just want it to be there. For example, when you install some packages that you don't need to do it again later, like ggplot2, you can put echo equals false. We can put eval equals false so that this chunk of code will not be evaluated when you export everything. it would just shown as a code chunk. There are a few different options, and also things you can define under this. Yeah, so this is the code chunk. And then something about the code chunk also is that if you only want to run this line, you can put Control Enter, similar to in the R script. But if you want to run the entire code chunk, you can put Control Shift Enter. That way, it will run all the code, like similar in the R script file. If you run Control Shift Enter, it will basically run everything. This is the code part for a R Markdown file. So we talk about R Markdown files. Other advantages is Kevin, I saw you raise your hand. Do you have any questions?
So sorry about that. You mentioned that if you wanted to run all of the code, it's Shift Enter.
Yeah, if you want it, yeah.
Yeah, but suppose I wanted to run this as a part of the code. I think this is true in R. Can I just highlight the code, only a section of the code I want to run, and then click Shift Enter?
Yeah, you can do that. That's actually a great question.
Okay.
If you don't want to run the whole chunk, but only like these two lines, you just highlight those and Control Enter. Yeah, that works. Any other questions? Okay. So that's the code part. About the text part, this is basically like a LaTeX syntax. You can put like different headers, for example, with this. I will show it in this tab.
Amber, I have a quick question.
Yeah.
This is gonna sound kind of ridiculous, but I feel like I generally use the notebook and the RMD files normally just like interchangeably. Is there any significant difference between the interface there?
The difference between R script and R Markdown?
Not the script, because you said that the Markdown, you said you're allowed to use text, but specifically, like, I think if you were to open up a new file, there's like Markdown, and then there's also like a notebook, if that's correct. So what's the difference between those two?
Oh, the notebook. I actually use them interchangeably. Let's see. Oh, can you see my screen?
Yeah, if it's not like if it's not notable to you, then we don't have to get derailed. I just wanted to ask if there's anything.
Yeah, most of the time I just use R Markdown. I did use R Notebook a few times, but I don't really see like a major difference that you choose one over the other. If anyone else has used like those two before and feel there's a huge difference, feel free to chime in. But as far as I used it, those two are pretty similar.
Thank you.
Yeah. So here, about the text in a R Markdown file, we talk about the different headers. So this is like the biggest text you can get. And then you can put a few text over here. Also in the R Markdown, you can put a link and you can put a hyperlink over here. It will either open a web page or it can open you can also insert a picture, for example, over here. You can insert like pictures over here. Also, if you want to just bold text, you just put if you just want to bold some text, you can put text and then it will be bolded once you render the file. I think to answer the question, so The notebooks are interactive. The output comes out right after each code. Markdown output is more for the final HTML PDF. Yeah, thanks for that. Okay. Yeah, so this is the line if you wanna put a hyperlink in the R Markdown file. And then I think for inserting a picture, it is somewhere down over here. Yeah, this is for inserting a picture into our Markdown file. In the GitHub page and the references, I also put a few cheat sheets about the syntax in R Markdown. So if you need them, you can take a look at it. Okay, another thing I want to cover about R Markdown, I believe is here, yeah. So in R Markdown, you can output it into different format. For example, you can knit it to HTML or you can knit it to PDF. So usually these two are, I think, are the most common ones. Here under the outline tab, if you just click on it, it will show like the outline for your current R Markdown. For example, I organized these R Markdown file in the current format because I use different headers and then the text of it. I think there is a way for you to convert a R Markdown file to R script or convert a R script to a R Markdown file. It should be just some. Oh, I think there's a question right here. Why would you use R Markdown or R Notebook instead of R script? Okay, that's a great question actually. Correct me if I'm wrong, but the script cannot be converted to a PDF. It only holds code. Yes. Yeah. Yeah, I believe that's correct. R Markdown can be converted back to script, but for script, it's code only. I'll double check that, but I think that's correct. And for the earlier question, for R Markdown, I feel like it's more easier to demonstrate graph and analyzing data set. For example, if you use a R script over here, when you run it, it's like basically prints out everything in the console. But for R Markdown file, when you render it, it also preserves all of the output. For example, if you take a look at the HTML file, over here. If you take a look at the HTML file, it preserves, it keeps like all the output when you run this code. That's, I think, is pretty helpful when you try to demonstrate or, yeah, pretty much demonstrate things like what this code returns. And if you export it as a PDF, I believe it's also the similar format, so it's easier. You don't need to run everything when you want to share or teach or demonstrate. Yeah, so I think that's the part I want to cover about getting started with our script and our Markdown. Let me see if there's any questions. Thanks for answering the question. Our Markdown produces a more reader-friendly narrative. Yeah. Thank you all for chiming in and share your experience with R and R Markdown. Okay, next, I think we're gonna cover a few operators in R. Yeah, so the first operators we're gonna cover is the assignment operators. So variables are stored in R's memory via the assignment operator. So basically you assign a value to, I'm gonna use the example here, it's easier. So basically when we run this, we assign this vector, this numeric vector, to the variable named A. Because we have run this whole chunk of code earlier for another example, now we can see in the end of the environment tab all of the variables defined. For example, with this line, we assign the numeric vectors 1, 2, 3 to the name A. And then with this line, this one is actually the right assignment operators. So you can either use a single arrow or a double arrow like this one. I think both works. Here we assign a logical vector to the variable name B. Here is the character vector defined using the concatenate function. And we assign this vector to the variable name C using the left assignment operator. Here is the right assignment operator but using the double arrow. One thing about the left assignment operators over here is that there are different ways that actually works. You can either use the like the single left assignment operator or the equal sign. So in general, both the arrow and the equal sign are works when you want to define values in the global environment. But there are some differences. For example, the use of the equal sign is restricted under some circumstances. We will talk about their differences later, but when you want to define a variable in the global environment, usually the left arrow is recommended. The second is the arithmetic operators. So these just do some mathematical calculations. Here, I added a few examples. For example, the add, subtract, multiply, divide. This is the reminder operator, and then power operator. Here are the few examples. So here for this line, we are basically calculating 2 to the power of 3. So this is also the power operator similar to this one. If you do 2 to the power of 3, I think it gives you the same result as A. Here for this syntax, we assign 2 to the power of 3 to the variable B. And using the parentheses over here, we are able to view the results. So we don't need to print or type B over here again. If we do not have the parentheses over here, for example, if we run the code like this with the parentheses on, we can view the results as B. If we do not have the parentheses over here and we just run this, it basically can only do the assignment. So we assign the value to B, but we do not print it. In this case, if we want to print it, there are a few options. You can just type in B here, so it will print the value of B in the global environment. And this is the subtract operator. So for this one, there's a recycling principle in R that whenever you have, here is a vector, and 2, this is a numeric. So when you do the subtraction, it recycles 2 to the same length as the vector. For example, over here, what it actually do is to create a new list, create a new vector the first element is 1 minus 2, and then the second element is 2 minus 2. For this line, if we run the code, is also the subtraction. It also element-wise subtraction, but because the length of the first vector is actually 6, so we have 6 elements in this vector, and we have 2 elements in the second vector. When we do the subtraction, what it does is it creates a new vector, and then it do the following subtractions: 1 minus 1, 2 minus 2, and then 3 minus 1, 3 minus 2, 4 minus 2, and then here it do 5 minus 1 and 6 minus 2. That's why we got the same length as the first vector. So here it does not have any warning because the longer object length is a multiple of the shorter length. We can take a look at the length over here via this function. This one is 6, and then if we just take a look at the second one, the length is 2. For this line, does anyone think there will be an error message or a warning if we execute it?
Well, I executed it and got a warning, so I would say yes.
Yeah. So the reason that it has a warning is because the longer object's length is not a multiple of the shorter length. I think it still gives you the output, but it also has a warning over here. So the output is 264, and what it actually does is that it creates an element, it creates a vector, and the operations, the first element is 1 multiplied 2, second element is 2 multiplied 3, that is still the element-wise multiplication, 2 multiplied 3, but then still following the recycling principle, there is no third element in the first vector, in the shorter vector, so it goes back to 1, even though the longer object is not a multiple of the shorter length. So the third element is actually calculated via 1 multiplied 4. So this one still gives you the result, but then it also outputs a warning. I think if you use our Markdown file, and then you do not want to show the warning when you render the file, there's a way you can put some arguments over here to avoid printing out the warning message. So let me take a look at the chat and see if there's any questions. What is the sign of the ink? Okay. Thanks everyone for typing the answer in the chat. Okay, if there's no other questions, I will go over to the next operations. So the next operation is the relational operators. I'm gonna close the outline over here, so it's maybe bigger. So the relational operators include some usual ones like greater than, less than, equal. For equal, there's like 2 equality sign over here. And then this one is for less than or equal to, greater than or equal to. And then this is the unequal. So let's take a look at a few examples. So for this line, does anyone have, maybe before running the code, do you think it will return true or false for this line? For true, you can just put in 1. For false, you can put in 0. Also here we use the semicolon to have multiple commands on the same line. Yes, someone put 1, so yeah, this one will return true. This is because the true is stored as 1 in R, and false is stored as 0. That's why when we try to do this, execute this line, it will return true for both line code actually. And then here, this one is actually comparing 2 vectors. Because in R we do, this is also a element-wise comparison. So we're here comparing 1 with whether 1 is less than or equal to 2, whether 2 is less than or equal to 3, 3 less than or equal to 4, 4 less than or equal to 5. That's why it returns true for this line. And then this one is the unequal operators we talked about earlier. So this one will also return true because 1 is not equal to 2, and so on and so forth. Next, we will be talking about the miscellaneous operators. So these are a few functions and operators that feel pretty helpful when working in R. For example, this line actually creates a series of numbers in a sequence. So 1 to 20. It gives you 1. It starts with 1, and then every time it adds 1 to the previous number until 20. Here is a little difference in R and maybe some other programming languages. If you use, I think Python, or it depends on how you index in those, but maybe in Python, I think it only prints out 1 till 19, but here in R, it actually prints out the 20 as well. If you want to print out a list of numbers, but not necessarily adding 1 each time, this one prints out 1 to 20, but adding 2 each time. Here, we do not have a 20 because if we use 19 plus 2, it's 21, and it is outside of the right-hand side. Another function that operator pretty helpful is the repeat. So for repeat 32, it prints the first element twice. You can also use a string over here, like A, and then it prints out A twice. Yeah, this one is for repeat with strings. Here, this is the to check whether 7 is in this numeric string. So this returns false because this is a numeric vector and 7 is not in it. If you change it to 1 in this numeric vector, it actually returns true because here it is. Okay, another thing I wanna briefly mention is that a lot of examples in this are Markdown file for, I think, both today and tomorrow. I used some of the variable names as just A, B, C, D. This is just for easier to demonstrate and easier to show, but I think when we do actual analysis, actual coding, this is not a good practice for assigning a name. You want to make the variable names as informative as possible. So for example, if you just use A, when other people take a look at it, they don't really know what A refers to. So yeah, just these variable names are just for demonstration only. So please don't use these as the variable names. Okay, so we covered the operations in R. Now we're gonna cover the working with R object section. So we talked about the terminal, the command line tool in R. For example, ls basically prints out everything under the current folder. And the current folder is, we can use pwd to show the directory we are currently at. In R, you can work with some similar functions. For example, ls. It prints out all of the variables that you currently defined. For example, previously we defined ABCD. These are stored in the global environment. So that's why when we type in ls, it prints out the names of all of those variables. We can also try to remove the R objects. So when we do, because we already defined A over here, so we can try to remove this A objects in our current R environment. So this one, yeah, after running rem A, basically we delete the A objects in the current global environment. If we try to type our ls right now, we only left with 3 R objects. Another thing with remove objects is that we want to clean up the current environment. For example, now we have defined 3 different variables, B, C, D, and now we want to clean the current environment. Maybe we want to rerun something. Then what we can do is to use rem list equals ls. That basically cleans up everything in the current environment. So now our environment is empty. And when we call A, we can no longer access it because it's basically deleted. If we type in help, this is a function I think we used earlier. It basically gives you the help page for EXP, the exponential function. Something similar is this one. If you just type one question mark, it gives you this helper page as well. These two are equivalent. And then if you type in example, EXP is the exponential function. So it gives you a few examples of how you can work with the EXP function in R. And then if you use the get current working directory, you can use this one. Sometimes you want to set a different working directory as your current working directory. You can do it in 2 different ways. The first one is to set WD. You can type your directory in the parentheses, so it sets into a different directory. Another way you can do it is by go to the session tab, and then here is the set working directory. You can choose the directory interactively. So yeah, these are a few tricks I think is pretty useful when you're working with R objects. Next, we are going to talk about the functions in R. So in R, at the very beginning, we talked about the 2 building blocks of R, the R objects and R functions. In R functions, there are a few different functions. So one main block of the functions are the building functions. So basically, you do not need to install any packages in R, and you already can access the functions. Some of the mass functions are building functions. For example, here we use the assignment operator to define a numeric vector, which is A. It has 2 elements, -1 and 2. And then we can try to find the absolute value of input A that will render 1, that will be a vector of 1, 2. Try to run those. You can see the results over here. And then the square root of input A, you can just type in sqrt 4. Yeah, the input is 4 instead of A over here. You can also find the natural log of input of input 10. Here is the common log of input 10. If at any time you find you forgot like how to use these functions, or you forgot the input for those functions, you can always type in the question mark and then the function name to take a look at the helper page. Some other built-in functions are the string functions. For example, here, the paste function, it basically concatenates vectors after converting to character. So here we have three elements over here. The first is a string of 1, the second is numeric, the third is a string of 3. So we see here we want to separate them by the comma. So it actually returns one element. If we take a look at the length of it, it is 1 instead of 3 in the previous. We can also split the elements of a character vector into different substrings. For example, we can use the string split function. This is our input is a string of, this is a line, and then we want to separate it by the empty tab, about the empty space. So this one will return 4 elements because there's 3 empty space separating the this string. So it will return this is a line, and because we separated by the empty space. If we put a comma over here, it will not do any substring because there's no comma within this string. Next are some statistical functions. Some statistical functions include the max function, mean function, sum function. For example, here, this chunk of code looks into the rnorm function. So if this is the first time you use the rnorm, you can actually type in question mark rnorm to take a look at the helper page. This is the usage for rnorm. And norm represent the normal distribution over here. And then dpqr are for density distribution function, quantile function, and random generator. So here we are generating 100 elements from the normal distribution. If we only take a look at this one, it will give you 100 elements. They are drawn from the normal distribution randomly. Range is one of the statistical built-in functions. If we run this line, it basically gives you the minimum value within your generated list, and then the maximum value within your generated list. This sounds right because for a normal distribution, it is not too small, too big over here because the default mean and SD is 0 and 1. Here we use the parentheses over here. So at first, it prints out the result of the range of our randomly generated normal distribution of 100 elements. And then it's stored it as r.x in the global environment over here. We can see r.x over here. We do not need to print it because we put the parentheses out here. These are a few built-in functions in R, but also you can define your own functions based on what you want to, based on your analysis or the data you have. So there are, in general, 3 steps in defining a function: its name, inputs, and body. So writing your own function has a few advantages compared with doing repeated work like copy and paste. For example, when your requirement or goal changes, you only need to make update in the function instead of in multiple places. So let's take a look at this user-defined function. in this function, we try to calculate the sum from the left-hand side to the right-hand side. So earlier we have used this syntax before. So it basically prints out from 1 to 10. We used 1 to 20 earlier. Then in the sum function, it actually takes the sum. It actually sum all of the elements for this list, for this factor. And then if we try to run this chunk of code, it returns 55. This is the same as we do sum and then 1 to 10. This gives the same result. So here, sum v2 is the function name. Input is a and b. So we use the input a and b consistently in this line and also in the body of the function. So this part is the body. Sometimes you have like a really large function that you have like a lot of things to define. The body part might be huge. But in general, it has these 3 parts: the function name, the inputs, and then body. Next, we will go over some of the packages in R. So earlier we talked about R package can extend the productivity, the analysis in R. So the R package is a collection of functions, data, and documentation that extends the capabilities of Base. The packages in the tidyverse share a common philosophy of data and R programming. So there are in general 2 steps when you try to install like a new package. The first thing you need to do is to install the package, and second, you need to load it. So for installing a package, the syntax is usually install the packages, and then ggplot2 the package name. So you only need to install the package once, but you need to load the package multiple times in the environment. For example, if you close the current session and you maybe open a new project, you have already installed the ggplot2 package, but so you don't need to do this one, but you still need to load the package every time you want to use it. We can also check the package version because R tends to update some of the packages every year, some of them from time to time. So it's usually good that you check the version of your package. So for me, I have the ggplot2 of version 3.4.2, and I have the dplyr 1.1.2. I think as long as you have a dplyr version greater than 1, you should be good. So here we use the install package to install one single package. If you have like a lot of package you wanted to install at once, you can define a package over here and then use a character vector to contain the package names, for example, ggplot2 per, and then you can install the packages all at once. Okay, so there's no question in the chat box, and we're going to continue. So sometimes if you have loaded multiple packages, there might be some function name that are the same. In that way, you might want to use the package name and then colon, followed by 2 colons, and then function name to indicate where your function comes from. For example, with the dplyr, with the mutate function, we want to use the mutate function from the dplyr package instead of any other package. So in this way, the program knows which mutate function to use when there are multiple ones. Yeah, so this is the packages in R. Tomorrow, I think tomorrow we will go over the tidyverse package. That is the open source package for our programming language. And I think that one is pretty useful for working with high data set to avoid spending too much time on data cleaning. So we will go over that tomorrow. Besides a lot of the commonly used packages, sometimes you might encounter packages developed by other programmers or other researchers. In that case, you might use the develop tools to directly download the package from their GitHub page. So every time you download a package, make sure that you check the version of it, because sometimes there are bugs reported, and if you always use the most updated version, sometimes it solves a few bugs, and see you sometime. Okay. Above are the part about packages, R objects, functions. Now we're going to move into the second building block in R, which is the vectors and augmented vectors. I think a few textbooks and resources introduce vectors differently in R, but here we are actually following the R for data science textbook, the section 20, because I feel like it is more intuitive idea of what vector is and how vector relates to other R objects, for example, data sets and table. So for the vectors in R, we will be separating them into vectors and augmented vectors. For augmented vectors, it basically refers to table and data frame. And for R objects, for vectors, it's the atomic vector and list. So we won't go into detail of the data structure in R, like the specific language that people use to call R objects. But if you are interested in the detailed data structure and data language in R, this will be the link to take a look at it. It contains all of the manual for our languages. So here, let's actually take a look at a very brief construction map on data structure. So here are a few concept maps. When we are going to take a look at the data types. Yes. So in R, the R objects are usually defined in two ways: their data type and also their storage type. The storage type are separated into like based on multiple angles. For example, the one-dimensional storage type, two-dimensional, whether all of the elements in your data are the same type, that'll be the homogeneous. If you have multiple data types within your data, then that'll be heterogeneous. We will go over examples of homogeneous and heterogeneous data type later in the next section. So for a list, it is basically one-dimensional. Both list and vector are one-dimensional data. That there's a plot later. But the difference is that for a list, the elements are heterogeneous, which means that the first element and second element might be different. For a vector, it is homogeneous, like the numeric vector we defined earlier, that we use concatenate 1, 2. In that example of a vector of a numeric vector, the elements are homogeneous because the elements are all double. So another commonly used storage type in R is two-dimensional instead of one-dimensional, like vector and list. The two-dimensional storage type includes data frame and matrix. Similar to list and vector, these two also differ by the element type. For example, in a matrix, you usually have the same type. For example, all of them are integers. Having a matrix has some advantages over using a data frame, because in data frame, it is more convenient because you have heterogeneous, so different types of data stored in a data frame. You can have both string and numeric type. But having a matrix, sometimes it's the computation is faster. We will also go over some examples of matrix later. So we talk about the storage type over here, and then for the data type, we introduced a few earlier, like the numeric, which includes both integer and double. For character, it is the more like the string type. For date time, it is the I'll actually have an example later, so we'll go over that. For logical, it is true and false. Different from Python, true and false are all uppercases. So in general, for both vector and matrix, those are homogeneous content, and R tends to work faster and more efficient with homogeneous, or what we call vectorized data. Getting back to the R script, we have a few examples on the atomic vectors, which is the logical numeric character vectors. So here we have, this one example is for the integer vector, and integer vectors has one special value, which is an A. If we type in type of A, we can see this one is for an integer vector. For a character vector, for a character vector, its element is a string, and a string can contain an arbitrary amount of data. For example, here we have a character vector with 3 elements. Each element is a string. If we run this code, it assigns this character vector to B. We can change it into like a longer string over here, but then the length of B doesn't change. It's still 3 because each of the string is actually one element. So there are 2 types of numeric vector. One is the integer vector we talked about here, and this one is a double vector. There are 4 different types of values, like 4 special values in a double vector. Those are NA, NaN, infinity, and minus infinity. So these are defined like this. So if we use this vector divided by 0, you can take a look at these 3 special values, the minus infinity, the NaN, and then the infinity. We can check the special values via the is NA and is in NaN function. So NA is NA, this is the is NA function. So it basically checks whether it is a missing value or not available value in your data set. So both NA and NaN are returns true and the is NA set function. We can also check the is NaN function. If we do this and the input is NA and NaN, I think this one returns false because missing value is not true and they're not a number, but NaN still returns true.
Sorry, please
That
repeat
means,
the difference. Please repeat the difference between NA and NaN.
do you mean the difference between NA and NaN?
Yeah, NA and NaN. As
So,
one returns false and one returns true. So what's the primary difference?
yeah, so NA is the missing value. So usually in a data set or when you do a survey, some people will not respond to a certain question. If you keep that cell empty, that will be an NA. Basically means no response or NA. There might be some systematic reasons to have a missing value in a data set. For example, maybe it is summer, so the weather or so if we have a column checking whether the weather is cold or below a certain degree, it's just NA because there's no observations under such weather condition. So sometimes missing values are caused by systematic reasons, and sometimes they're just caused by the design for survey that you're not getting enough information. But for NaN, like how we define, it is actually representing not a number. These only applies to, I think, numeric values, and these apply to numeric values and also real and imaginary part of the complex values. So usually we work with missing values, so NA more often, but it's useful to check whether you have any not a number value. This happens sometimes in the conversion when you coerce a number between different types. Sometimes you might have it. Yeah, so NA is the missing data and NaN is not a number. You can always remember it by how you got it in the end, like 0 divided by 0. That gives you not a number. Next, we're going to introduce the logical vector. Logical vector is also under the atomic vectors. So the one special type is also NA. It does not have the NaN. So NaN, the not a number, only happens in the numeric, only happens in the double vector over here. So here we define the logical vector with true, false, and one missing value. Here we can take a look at the type of each vector and then the class of each vector. For the integer vector, the type of it is integer and the class is also integer. But for the character vector, oh, I have a lens of it over here. Both this type of and class are character. For the double vector, it's different. So the type of the double vector is actually double, but then the class of it is actually a numeric vector. We talk about numeric vector includes both integers and doubles. And then D is the logical vector, so both the type and class are logical. There is one tricky part about working with doubles, so basically decimal numbers in R. It's pretty similar to other programming language like Python. So if you try to run this line of code, it actually returns false. This is because R stores the value differently. Square root 2 is actually not equal to this number, even though if you just run square root of 2, it returns this, but it actually stores differently. So one way you can compare double with a double, double with a double is by using the dplyr near function. So we can take a look at the helper page for this function. it basically compares two numeric vectors of floating point numbers. We need to specify the tolerance, like how much tolerance you have over here. I think the default is pretty small. Yeah, if we do not have the tolerance over here and just run the near function, it actually returns false because the tolerance is too small. If we put it back, it actually returns true over here. This is because if we have 0.001, 0.001, yeah, the first 6 digits for this decimal are the same. That's why when we have a tolerance of it, when we have a bigger tolerance, it returns true. So that's the part to remember of working with decimals or doubles in R.
Sorry, I had a quick question. So I noticed when you talked about types, right? So you have integer, character, doubles, but I noticed you didn't use an example with strings. So like if you have qualitative data, how does R treat strings?
For strings,
Strings, like if you had a data set and it had like gender, or like a data set that had like race or something, and you have like, yeah.
Yeah, that's a great question. So basically when we're working with factors, right? I have one example over here actually about working with factor. So factor is also a special type of list. We can define it here. So if we have like a character vector of female, male, female, okay. So this one is the character vector. We define it and we use the A as well. And then we can convert it to a factor using the factor function. Yeah. So in this way, we define the a factor of 2 levels, female and male. We can take a look at we define this factor as B, so we can take a look at its type of and also class. So because factors is a special type of list, it is actually stored as integers. Even though the elements of it is a string, it's stored as an integer. That's why when we use type of this factor, it returns integer. But for if you use class, it's actually returns factor. So factor is another example that is type of and class are different.
And the integer value that are automatically stored, is it as, will it store it as like female 1, male 0, or will it just do 1, 2, 3?
I think the default is 1, 2 instead of 1, 0. But you can always re-level the factor levels. For example, here, because F is alphabetically before M, that's why this one is 1, this one's 2, but you can re-level it so that male is actually the first level, the base level, and then female is the like the second one. Yeah, so
thank you.
Yeah, of course. So after the atomic vectors, over here, we're going to talk about how to add the elements to a vector. So here I should specify this is adding an element to a atomic vector. If we try to run this line of code, even though it has like a really complicated structure, that we are creating a vector using multiple concatenate function, but actually it just returns one plain numeric vector with integer values. So these actually returns true because this one is the integer vector we defined earlier, and this one actually returns a flat vector as well. So we can So yeah, for a vector, it does not have a tree structure. We will talk about tree structure in later in the list. I skipped the part about adding elements. So here in this line, we define a vector of integer vector. It has 11 elements, 1 to 10, and then the last one is an A. So if we want to add 11 to the end of the list, we can always use concatenate A, which is defined here as 1 to 10 plus an A with 11. So that creates a new vector. So it updates A with 11 at the very end. So coercion. So there are in general two types of coercion. The first one is explicit coercion, and I think the second one is implicit coercion. Explicit coercion happens more rarely. It happens when you call a function like as logical or as integer, as double, as character. So you should always check that you can mix that specific fixed upstream. Sometimes there are restrictions on what type can be coerced to what type. We'll go over a few examples over here. So as we talk about true equals 1 in R, if we use sorry, this is still logical. So here we have a string of true, and if we convert it to a logical vector, we have like just the logical true. And then because we talk about 0 is interpreted as false in R, so if we run this, it will return false because 0 is basically equivalent to false here. And then because 1 is interpreted as true, if we run as logical, we coerce it to true. Actually, for in R, for any integer larger than or equal to 1, it always coerced to true and they're as logical. So we can also convert a few different numbers, double to integer. For example, with as integer function, it truncate this decimal number to only the integer part. So for 1.2, it's coerced to 1, and for 1.9, it coerced to 1 as well. Something that happens more often is the implicit coercion. So implicit coercion happens when you have a specific context that expects a certain type of vector. For example, when you use a logical vector within a numeric summary functions, the implicit coercion happens. We'll take a look at this example. So here we have a logical vector, basically true, false, false. And we know that true is interpreted as 1 and false interpreted as 0. So when we try to use the sum function, it coerced these three elements implicitly. So actually, if we run this code, it will return 1 because true is 1, and then true, false are both 0. So the sum of it is still 1. Also, the main function will have some implicit coercion as well. As earlier, true is 1, so false is 0. We're basically calculating 1 over 3. That's why we have a logical vector as input, but after the numeric function, it returns like a double. We talked about the relational operator earlier, but this one also has like some implicit coercion. For example, if we do this, it will implicit coerce this string of 2 to actually the integer 2. So that's why it returns true. Here we have a few. This example is example of implicit coercion. So here we use the rnorm function. We generate 100 samples from the normal distribution with mean 0 and standard deviation 1. So these are our vector of 100 elements. And then for this line, we look at which one in X is greater than 1.96. So using the recycling principle for R, we are basically comparing each of the element stored in X with the value 1.98 or 1.96. So it will return a logical vector, some are true and some are false. Then we calculate the mean of it. So that'll be the proportion in X that is greater than 1.96. This one is slightly smaller than 5%. This is because we only look at the values greater than 1.96. We do, and we're not looking at like both the values greater than or less than 1.96 and less than minus 1.96. That's why it's slightly smaller than 5%. Here we use set seed. You can just put a random number over here. If we do not use the set seed function over here, every time we use the randomly generating function, it returns a different X. For example, oh yeah, I already run the set seed function, but if we don't run the set seed function, each of the time you have a different X generated. Here we have a few more examples on the coercion. So the first line we run type of 1, type of 1L. These are different because if we want to specify we have an integer, we have to put L over here. And this means like an integer, but this one means a double. And then we have type of C, true 2L. So we already know the type of 2L is an integer. However, if we run a vector, if we run the type for concatenate logical and integer, I think the result is an integer. If we have a vector containing integer and double, the type will be double. And if we have a vector with double and character, the final type of will be character. This is because the most complex type always wins. So the types from least to most complex are logical, integer, double, and character. As long as you have a character in your vector, the type of will always be character. Okay. Yeah, next are just a few examples of working with vectors. Yeah, I should specify this is atomic vector, not list. So here we can check the type of vectors. So here we define a integer vector. If we run type of double, it actually returns. Oh, it actually returns double because we didn't specify these inputs are integers. If you want to find a integer vector, you have to use 1L, 2L, and then 3L. That's why if we run type of, it returns a integer. So we can also check whether this one is double, is of type double. I think there are some basic functions, like base R provides some of the functions in the format of is vector or is logical, but some of them has a little surprising results for certain types of inputs. So it's safer to use the is underscore function provided by Perl. So if we run this, it will return true because we defined it in 1, 2, 3 instead of 1L, 2L, 3L. And then this is the vector recycling that we talked about earlier. Here it interprets 1 as a vector of 1 element. On the left-hand side, this actually generates samples from a chi-squared distribution. So similar to our norm, our chi-squared generates examples, I generate samples from the chi-square distribution, and I put the degree of freedom 2, but you can put in like any other degree based on the data and distribution you have. So these are the 100 samples generated randomly from the chi-square distribution with 2 degrees of freedom, and I want to look at which one of them are greater than 1. That's where vector recycling coming in. So each of the elements is compared with 1, and if it is greater than 1, then it returns true. If it's not, then it returns false. So yeah, this is the output after running this code. Next, we have one thing just to mention is here. So R don't actually have scalars, but instead a single number, for example, like 1 is a vector of length 1. So this one is actually the length of the left-hand side is actually a multiple of the right-hand side because this is of length 1. So it can always do the vector recycling without causing any warning message. And then here we have the vector names section. We talked about the assignment operator using the arrow sign and also the equal sign earlier. Now we can see what is the difference of it. What is the restriction on the equal sign? So if we have something like this, we are basically creating a integer vector with 3 elements. We are assigning the first element name is XX. The second element has name YY, and then the third element has name ZZ. So these XX equals 1, YY equals 2, ZZ equals 3 are not stored in the global environment. You can take a look at here. So even though we use the assignment operator over here, they are not stored in the global environment. However, if we run something like this, we change the equal sign to the arrow operator. It actually assigns 3 to ZZ in the global environment. You can take a look here, the last line. So now ZZ is 3 is stored under the name ZZ. However, it is not stored within this function. So C is actually a function. It's a generic function for combining different arguments. And that's why we usually use the arrow sign in the global environment. For example, we assign like A equals 2, and then B maybe equals 3. But within the function here, we use the equal sign so that we don't store too many variables or values in the global environment. It is only used within this environment. So always remember, if you are defining, if you're a break-in, yeah. I will go over the subsetting vector section and there will be a break. So here we can look at the names for the vector. So here we define X as a integer vector with 3 elements, but it does not have a name because we didn't assign maybe XX equals 1 or YY equals 2. So it doesn't have any names for this one. If we define it as this way, the way we talked about earlier using the equal sign. Yeah, why do you use 1 equal sign instead of a double equal sign when defining the vectors? That's actually a great question. So we talked about the equality sign earlier with 2. This one is actually checking whether the left-hand side is equal to the right-hand side. It is not a assignment operator. If you use 1 equals true. I think this errors out. You have to you can use this. So 1 equals so the single equality sign basically means we are assigning the value of the right hand side to the left hand side. But when we use a double equality sign, it actually checks whether the left hand side is different from is the same as the right hand side. So I think if we use now it's not here. Okay. So these actually are different operators. Okay, so we were talking about this one earlier, and I think we went over the names of y already. It is not stored globally. XX is not in the global environment, but XX is actually stored as the name of y. Here we will just quickly go over subsetting vectors. So the index in R starts from 1 versus the index in Python actually starts from 0, but it also depends on how you index it. This one is the example of a character vector. So we define CHR as a character vector of A, B, C, which are strings. And then if we use CHR1, it returns the first element of CHR, so basically A. We can also select 2 elements from a vector. We can use this syntax. Basically means we are selecting the first and second element from CHR. And here we are selecting 4 elements from CHR, the first element. So we are selecting the first element, second element, first, second from CHR. That way we can actually make a longer vector compared with the original vector by indexing it multiple times. These 3 lines are indexing using a positive integer. If we want to use a negative integer, this means that you are selecting the value at every position except the first position. So if we want this, it will actually return B and C. However, you cannot use this syntax of a mixture of positive and negative values. Either you use all positive or negative to indicate that you are not selecting this index. If you assign names for the vector, for the element in the vector, for example, with this one, the int, they say you are creating an integer vector, whereas each element has a name, then you can subset in the vector using the name of it. So basically XX is 1, so it will return this. Yeah, these are the sections for vectors. We will take a break for 10 minutes. If you have any questions, feel free to put it in the chat or unmute yourself. Okay, so we just talked about atomic vectors in R. And another type of vector in R are the list. So those are also called recursive vectors. Later, maybe tomorrow, we will talk about trees. So list can actually represent hierarchy or tree-like structures, which is different from a vector. Those are just one-dimensional. So let's take a look at the list over here. Yeah. So we define list pretty similar to a vector. So remember, we define a vector only using the concatenate function, 1, 2, 3. We define a list using the list function. So here we are defining a list of 4 of 4 elements. So the reason it is 4 elements is because we're using the comma separated to separate the inputs. So the first element is the integer 1, 2, and then a string of A. And then lastly, we have a vector from 1 to 10. Yeah, the integer vector from 1 to 10. That's why if we take a look at the length of it, it's actually 4. One way to look at the structure of a list is by using the structure function. So we can actually try something like this. So f is defined by list 1 to A, 1 to 10. So these are the 4 elements over here. In the list, earlier we looked at the picture of the data types in R, where we talk about for a list, it is heterogeneous, heterogeneous components, meaning that each of the component can be of different types. So for example, here, the first component is of type numeric, and then the third element is actually the string, and then the fourth element is actually an integer vector. We can also create a list via by inputting the vectors into it. So remember, we define A as 1, B as a string vector with 3 elements, A, B, B, and C. And then we define C as a double vector, so basically contains a few decimal, and then 4 special types for a double vector. So if we use the list function and put those 3 elements as input, it basically returns a new list. It has 3 elements, A, B, C. The first element is the 1, and then second element is a character string, character vector, and third element is actually a double vector. So actually let's take a look at a very complicated list example. And that can give you a brief idea of how it can construct and represent a tree structure later. So here, let's define the complicated list first. Again, this name is not a good example, but just for easier to demonstrate. So here we are defining a list structure with a few elements. So the first element is 1, 2. That means a vector from 1 to 2. The second element is a integer vector that we defined before. And then the third element is actually a string of A. The fourth element is a single string B. The fifth element is actually a character string that we defined that we talked about earlier. It has 2 elements separated by the comma here. The first element is the string A, and the second element, even though this is pretty long, because this is a single string, it is still considered as a single element within the character vector. What is tricky about this is the last element. So here we are defining a vector over here. So C, concatenate, and then 3 elements. The first element is a integer which is stored as a double. The second element is a string. The third element is a logical. So according to before, when we talked about coercion, the implicit coercion, the type of this is actually character because it's character because character is the most complex element within this vector. However, we are also assigning names to the element of this one. So we are assigning we are assigning XXX to 1, and we are assigning ZZZ to this very complex character vector. So let's take a look at a structure of how to interpret it as a tree. So as we this is how we defined it. There are 6 elements, so we can view it as like a one-dimensional at the very beginning with 6 elements. At this point, we don't know what element each of the boxes. It may be like a vector with integers. It may be a single string, or it may be a very complicated list. We're only looking at the most complex one, so the last element of this list. That is ZZZ equals concatenated XXX equals 1, and then a string of A, and then a logical of 2. So the last box over here actually points to the ZZZ object over here. We are defining it as a vector. It is actually a character vector. So when we use complicated list, bracket 6, meaning that we are trying to look at the index 6 element within complicated list. So it points to this box. We know it has a name of ZZZ. And because the hierarchy, we actually know everything below it. So we know that it has, so we know this ZZZ object has 3 components in it. And we actually know that the first component has a name of XXX, and then the second component, third component actually points to different things. So at this point, if we use complicated list, bracket 6, we know everything below it. If we try to look at the closures, that means we are using the double bracket over here. So complicated list, double bracket 6. This means, so the first bracket 6 here, we are pointing at this box, this yellow box. And then if we use a double bracket, we are actually look one level deeper, which means we are going to this level. So we are look into what ZZZ is. And if we are in this level, we do not know the name of it already. A more visual way to see it is by taking a look at this. So in the yellow box level, we are looking at bracket 6. So basically it gives you everything below it. So we have ZZZ, we have the 3-element box, we have the 3-element vector, everything below it. However, if we use a double bracket over here, we do not see the ZZZ. This means we are looking from this level only. We can see everything below this level. So basically everything in orange. This is the same as complicated list. We use a $sign and then ZZZ. Why we use a $sign? Let's take a look at the structure of complicated list. In complicated list, we have 6 elements. We can access each element using the $sign. So for the first 5 elements, there's no name assigned to it. So here is not. However, for the last element, we have the name ZZZ. And when we use complicated list, $sign, ZZZ, which means that we are looking at ZZZ, but then we are one level deeper because we're actually looking at everything below this level. That's why we have everything orange. And these two are actually giving the same results. If we want to look deeper into it, we're already at this level. So we know that under this level, we have a 3-element vector. So I want to look at the first element within this vector. So we have complicated list double bracket 6 over here from the orange to below. And then if we put single bracket 1, meaning that we are looking at the first element. Because this is a single element, this is a single bracket, we're not going any deeper. We are still at this level. So when we point at this, we are basically pointing at the green box over here. So if we point at the green box over here, we can see the arrow only points to like anything below it. However, we can still access the information from this green box and this green box. If we put the double bracket over here, meaning that we are going one level deeper. So if we from a single bracket of 1, we are here, and then put a double bracket, we know there's only one arrow over here, so we have to go to this last box. And in this last box, we do not know the name of the green box anymore because we are at one level deeper. So that's why we have complicated list, double bracket 6, 1, and double bracket 6, double bracket 1. And these two actually returns different things. Here is what it returns using a single bracket. So we are not going any level deeper. We still know the name for XXX. Here we are actually going one level deeper and we no longer has access to its name. That's the box at the very bottom. So if we use the leaf and root. Oh yeah, Kevin, do you have any questions?
Yes. Hi, Amber. I'm so sorry to cut you. So a little bit. So my only question about these complicated lists are that you'll have data that will have basically different types, right? You have integers, you'll have double, you have all of these different things. Why is it that the data then these lists will be on like multiple levels? That's what I'm trying to figure out. Or you have to call to each level. Can't you just keep it as like a separate thing, or why is it like at all off these levels? That's the only thing I'm kind of like not really understanding.
Yeah, thank you so much for the question. Actually, it might relate to tomorrow's material as well about the tree structure. So let's think about one example using states and county in the US. For example, if you have, for example, within US, you have different states like California, but then within California, you have different counties, maybe like Orange County or like other ones, I don't quite remember. So the way that we organize it is by a hierarchy. So county is like the biggest one, and then within county you have different levels, like states and county. So when we do like a tree, when we try to use a tree, for example, you have like the number of people for each county, and then you have the number of people. And once you have the number of people for each county, you can calculate the number of people for each state, and then you can calculate the number of people for the whole country. So using a tree structure, you can actually look at whether it is a balanced tree or not. That means you have the total population for the US at the very top, and then you can separate it into multiple states, for example, California, New York, and then you can take a look at the population within each state, and then you can look at the population within each county. So that's the base level. What we can interpret from that is that whether the tree is a balanced tree or not. So for example, you can group a few states, maybe like Western states or Eastern states, the middle ones, the northern ones, the northern ones. And you can take a look at whether this is a balanced tree, meaning that once we group them by like different regions, the Western Pacific or the Eastern, whether they have this whether similar number of populations for each of the region. If they are, if we have like a balanced tree, meaning that the grouping are basically each region has similar population. But if you have like an imbalanced tree, meaning that, for example, you have 50% population, you want to have 50% population in the region, but then you need more, you are covering more region in the western coast versus the eastern coast because the population density is different. So that's what we can do with the tree and how we can maybe interpret the tree. But this definitely depends on what your research interest or what your goal is. I will try to put in more examples of the tree structure and hierarchy structure tomorrow using R. Yeah.
Okay, thank you so much.
Yeah. So I think we just went over the list over here. Okay, so and then this is the structure of the tree structure, the hierarchy that you have like the highest level and then all of the base levels. Let's go back to the script over here. Yeah, so these are like accessing different levels of information, and it is different. So in most of the cases, it shouldn't make you worry about it, but sometimes some functions or some packages require a specific type or specific level. That's why we might want to pay attention to like how to access different levels of information with either double bracket or a single bracket. This one is also creating a list, but we are creating a list. This is like a really balanced tree if we think about it that way, because we have a list of 2 elements. So basically think of a tree with 2 elements, one on the left-hand side, one on the right-hand side, and each of the element has 2 elements below it. So 1, 2 on the left-hand side and 3, 4 on the right-hand side. So this is pretty balanced. We can still use structure to take a look at the structure of the list. Here, these two are actually different. So so here we use the concatenated vectors as the inputs for the list, and here we use the list as the input for the list. The second one is a more complicated structure because we have 1 level deeper, and this one actually only 2 levels because vectors are 1-dimensional, and here we are creating a 2-dimensional list. Yeah, so these depends on your data set. If you have like a data set that has multiple levels, you might want to use a more complicated structure. Okay, now we're going to talk about the coercion for vectors and coercion, the coercion between vectors and list. So why do we need that? For a few functions like mean function, it actually expects a certain type of input. For example, for the main function, it expects a numeric or logical vector and datetime and time interval objects. So that does not include a list objects, meaning that if we create a list of 1, 2, 3, we cannot pass it to the main function to calculate the mean of it. It will erroring out because a main function is actually expecting a vector input instead of the list input. In that case, we can convert our list to a vector via the endList function. So this turns a list into an atomic vector. So this is our int that. Yeah, so here we deliberately convert the vector to a list via the addList function. But here we are converting the list back to a integer vector. Because of the implicit coercion, actually it converts back to a integer vector, more broadly the numeric vector. So now we can actually use the main function on it because now it is a vector and we got output 3.5. And like before, if we use main function on ls, so ls is the converted list version of the integer vector, we are actually getting a warning message. So sometimes we got a warning message, it's usually helpful to look at this one, like it is telling you the argument is not numerical logical, then you can check what is expected for this function, and you can fix the issue. Okay. Here we can take a look at how to subset a list. So subsetting a list and subsetting a vector might be different depending on the double bracket or single bracket. But in general, the idea of the same, you are indexing the list of vectors with this syntax. So we're still using the complicated list example from earlier. This is the structure of the complicated list using str function. So if we use complicated list 1, 2, 3, meaning that we are trying to extract the first 3 elements from the complicated list. And in this example, we are extracting these 3. So the result will still be a list. If we want to take a look at it, we are extracting the first 3 elements from it. And from the structure, you can easily see this is still a list instead of a vector, because they have heterogeneous components in it. If we use complicated list number 6, that's the example from the actually from the picture earlier. So we are looking at the 6th or the last element in our complicated list. That is a ZZZ. And remember, we are using complicated list 6 with a single bracket. So it looks like we can still access its name. And then we can look at everything that is in the level below it. So basically we have everything here. Versus this line. So this line, like the picture above, we are extracting the information 1 level deeper. So basically we're using 2 brackets over here. We no longer have access to its name because we are looking at only the base level. And from the example above, we know these 2 actually return the same because using the $sign and using the $sign's name, actually we are already going one level down, and then using the double bracket, we are also going 1 level down. This is example for accessing the first element within the last element for the complicated list. These 2 are different as well when we talk about using double bracket and single bracket over here. So using double bracket over here, we do not have access to the name of it, which is XXX. Whereas if we only use a single bracket, we still have access to the 1 level upper information, which includes its name, so XXX. So here, list is actually more used more, I think, in R compared with vectors because it's more versatile, containing heterogeneous information. For example, if we want to do like a linear regression, which is under LM function. So this is under stats package, and the LM function basically allows you to fit a linear model. The inputs are here. So we are trying to fit a linear model regressing MPG on CVAR-L. We can look at the specific meaning for the columns. So this is the empty cars data set. And then we can take a look at these columns by using question mark empty cars. Then it brings us to these data set. So this is a description of what this data set is. So basically we have 10 aspects of automobile design and the performance for 23 automobiles. So we have 32 lines. And in the format, we can take a look at the variables and observations. So observations refer to the row over here. So this line is 1 observation. This line is another observation. This line is an observation. And then the columns are variables or attributes. So I think the terminology is a little different in statistics and machine learning. But as for using R for most of the time, we are still referring to the rows as observation and columns as variables or attributes. So here we are basically building a linear model on the empty cards. We can take a look at it. Some of you might already be familiar with running linear regression in R. We can use more complex models, such as the generalized linear regression models. But here we are only using it for the demonstration of the type. So basically, we if we want model, because if we define a model this way, we can have access to different informations. So this is a list containing multiple elements. Each element is not necessarily a vector. It may be a list, or it may be like more complex structures. So if we look at the length of it, it returns the length of the list. So basically the length of the model. It has 12 components. We can access its individual components by using model $, and then we can choose which one we want to look at. For example, the coefficient or the intercept. And then we talk about checking whether our input is a list or not using the Perl is_list function. So this is because the base function in R, the is.list, sometimes returns very surprising result. That's why we try to avoid those using a more stable version, which is Perl colon is list. So this one will return true because our linear regression object is actually a list. So this example of list, we will examine it deeper tomorrow with more examples. Next, we have factors. So factors are a type of the augmented vectors in R. Factors are built on top of integer vectors. So actually we looked over one example earlier when we define a factor and then we call type of function on this factor. It is actually integer. So factors are usually designed to represent categorical data. So for example, with the gender data, you have male, female, or you have the states data, you have different states, and each state is a different level. So the categorical data can usually take a fixed set of possible values. And factors can be ordered, which are ordinal variable, or unordered, which are nominal or categorical variables. Using factors can also be used in the linear regression or generalized linear regression models, and also in plot methods. We'll go over the models related to categorical data in tomorrow's session. I think earlier, in maybe like previous versions, most data loading functions in R automatically convert character vectors to factors. That is when you want to load a data set, maybe like the empty card.csv data set that you downloaded into R. It will load the character vector, so the column, like a variable, the variable of a column as a factor. You can avoid that by using this. By including this argument within the read.csv function, but I think it is no longer the case for the current version of R. However, if you still have the previous version of R, you might want to use this argument to suppress this implicit coercion between vectors to vectors. Okay, so this is the example for a vector. We can define it. Here, here we're actually converting a character vector, the ABB BC, into a vector. Oh, actually, redefine it as a ABCD. I forgot to put it here. So we can then define our vector via this. So vector is a special type of vector, and as we tried this example earlier, if we use type of, it's actually integer, but the class is still a vector. So we can take a look at the structure of our vector via the str function. So here it's saying that our e variable is basically a vector with 4 levels. So A, B, C, D. I think it represents the base level as 1, and then assign 2, 3, 4 to the other levels, and then this is the base level because it is like A before BCD in the alphabet. You can always re-level a vector using the, I think it's the re-level function in R. We can also take a look at the attributes of a vector. So it has levels, A, B, C, D, and then it has class vector. You can always add more attributes. For example, like I want to put a name attribute, and then the name is K. That's why we are actually adding a attribute to E. So when we run attributes of E, we have one more component, which is a name component. Another type of augmented vectors in R are the matrix. So matrix is pretty useful when you do calculations, and also when you have large amount of data. So when you do machine learning, sometimes you will have to convert your input into a matrix form. That is usually where matrix come in. If you want to know how to define a matrix or convert a vector to a matrix, you can always use question mark matrix to take a look at the helper page. So here our input is 1 to 8, and we want to have 2 rows, which means we want to have a 2 by 4 matrix. We only need to specify either number of row or number of column to define the matrix. So let's take a look at what the matrix is. So this is a 2 by 4 matrix, and then the type of the matrix is actually double. Even though these are integers, we are not putting L. We're not using 1L, 2L, 3L, so this is still a double type. I think matrix have a few more attributes. It has dimensions. So dimensions means that the number of row is the first dimension and number of column is the second dimension. You can always look at the transpose of a matrix by using T function. So for a more detailed explanation of what T function is, you can take a look at this. So these are pretty useful when you do more calculations in the matrix form, especially have really large data set. So subsetting a matrix is pretty similar to the previous ones, as you are using bracket. So here in the bracket, before the comma is the row index, and after the comma is the column index. So basically you are putting the index for the rows first, 1, 2, 3, 4 first, and then you are putting the index for the column second. We can take a look at what these two return. So matrix bracket 1 comma is returning the first line. This is because we are saying that this is matrix. So using this line, we are saying that we want the first row of the matrix, but we do not have any constraint on the column. So we are returning the first row. And then this line is actually saying we do not have any constraint on the rows, but we only want the first column. That's why it returns 1, 2. So yeah, subsetting matrix and list
Sorry,
is
could you
pretty
repeat that, please?
yeah,
Where
yeah.
it returns 1, 2, in particular, the second line.
Yeah, sure. So here we are trying to subset the matrix using this syntax. So the inputs before comma is the row, and then the input after the comma is our constraint on the column. So because here we don't put anything in the row section, we're basically having no constraint over which row we want to select. But here we are putting a 1 in the second argument, meaning that we have a constraint on the columns of the matrix, and in specific, we want the first column. So this 1 is actually the index for the column. And because no constraint for this, no constraint for rows, only constraint on the first column, we are actually looking at this part only, so 1, 2 element. However, we can also subsetting for multiple columns using this syntax. So these two are similar. The only difference is that here we only want to select 1 column, so we only put 1 over here. But now we want to select 2 columns, so we want to select the first column and then the second column. This one will actually return these 4 elements, because as before we have no constraint on the rows, and we want the first 2 columns over here. So that's why we are returning a 2 by 2 matrix using this syntax. Any other questions? If not, I'm going to continue to the next type of augmented vectors, which are dates. So dates are actually represented as actually stored as vectors here. For example, if we use if we put this string over here, it is a string, a character. But if we use the add date function, this is the explicit coercion. So we are converting a character, a string into a date object. And we are actually storing it as date time. So date time is over here. We can take a look at this. This is stored in the global environment. We can take a look at what type of the date is. It is actually a double. So so days and date times are built on top of numeric vectors. That's why it is a double instead of an integer. And then we can also look at the attributes of it. So pretty similar to before. When we access it, we can see the class of the date time is actually date. This is because we converted this string to a date earlier in this line. So S date 1971, January the 1st. That's why the class is date. The type is double because date times is built upon the numeric. It's built upon the double vectors in specific in more general the numeric vectors. I think we have 2 other types of augmented vectors. The first type is the data frame. That is, I think most of the time we're working with data frames or table in R. And data frames are built on top of lists. So the difference between a table and a list is that all the elements of a data frame must be vectors with the same length. So remember, we defined a very complicated list earlier. We have 6 elements, and however, each elements are of different lengths. The last element has a length of 3. The 5th element has a length of 2, and then the 4th element has a length of 1. This cannot happen in a data frame. So basically, in a data frame, we want all of the vectors, all of the columns to be of the same length. So we can actually take a look at this example. Here we are defining a data frame. We can take a look at how this function is defined using the helper function. So this is the input. So x is 1 to 5 and y is 5 to 1. So that gives you 2 columns we defined using this line and this line. Remember, within the function, we are using the equal sign to assign values instead of the arrow sign. If we define it using the arrow sign within the function, for example, if we change this one to the arrow sign, it will be different because we can take a look. This one is actually defined globally. So if we look for y over here, it is defined in the global environment from within a integer vector of 5, 4, 3, 2, 1. So always use the equal sign when you are assigning values within a function. So here the function is data frame. So because we said earlier that data frames are built upon list. So if we use a type of data frame, it is list, and the attributes of data frame contains the names, class, and row names. So what are the names? Names here actually refers to the column names of the column name of df. So because we assign x and y over here, these two are actually the column names. The row names, we do not assign any row names in this example because there's row name argument, but we're not assigning everything. So the default is 1 to the number of rows. We can always change it using the arguments within the data frame function. Now let's define a more complicated data frame example, the df2. So here we are defining 3 lists over here. Each list is of equal length. So for example, for ID, it is a character vector of length 3, and gender is a factor of length 3. Grade is an integer vector of length 3. So it has to be the same length. If you accidentally put 80 over here, the last vector is actually of length 4, then you will have an error because data frame expects the length to be the same. However, earlier in the picture, we talked about different types. We said that data frame and matrix are different in the sense that data frame can contain heterogeneous contents, meaning that the contents can be of different type. So that is true over here because if we take a look at df2, this column is of integer, is of double. And then the gender column is actually a factor. The ID column is a character vector. So those are of different types, but we can store it in the data frame. We cannot store it in a matrix because the contents are of different types. So if we take a look at the types of, it is a list because data frame are built upon the list. We can take a look at a class. This is a data frame. And then we can take a look at a structure. So This is pretty similar to a list structure because data frame are built upon a list. We have 3 observations and 3 variables. This is because we have 3 rows that represents 3 observations. We have 3 columns, that means the 3 variables. And the content are heterogeneous, meaning that they are different contents, for example, the string, and here we have numeric, a specific, a integer, a double. So how to subset a data frame? We can always use a $sign to extract a single column. Let's take a look at df2 $sign. If we put $sign here, we can use it to access the 3 columns, maybe like ID that gives you the first column, and we can use $sign gender that gives you the second column. And our second column is actually a factor with 2 levels, female and male. This is equivalent to df2 using the bracket notation. So df2 using double bracket notation 2 is actually looking at the second column because the index is 2 over here. But we have to use a double bracket. We can also use, so for example, if we use the single bracket, it works, but it actually returns something different. Let's take a look at why it is different. So I of df2, if we only use a single bracket, this returns a list. Whereas if we use a double bracket, it returns a vector it returns the integer vector. This difference is actually pretty tricky because remember earlier we talked about the main function, and the inputs of main functions are vectors. We cannot use list for the main function. So let's take a look. If we only use the single bracket, which returns a list, it will error out. But if we use a double bracket, this one also errors out. Let's see. Oh, df2. Oh, because the second column is actually a factor, a gender, it's not numeric. I think I changed this example earlier. That should be this third column. So it is not gender, it is grade. So we can use a $sign or we can use a double bracket so that we are actually returning a vector instead of a list. Whereas if we use the single bracket, it will error out because the a single bracket looks as 1 level higher, so that's still a list. That's why when you want to extract a single column, it is safer to use a $sign or a double bracket. Similar to the matrix subsetting, we can also subset a data frame using this notation of like a comma separated parentheses. So let's take a look at this one. So here, using the syntax, we are looking at a subset of df2, whereas we have no constraint over the rows because this is empty over here, but we have constraint over the column because it's the second argument after the comma. We only want the first 2 columns of it. So we actually subsetting the ID column and the gender column from df2, but we are returning all the rows because here we have no constraint. This actually returns the same information if we use this syntax. So we can use these syntax when we have a consecutive constraint on either the column or rows. Also, another thing another syntax returning the same information is this one. So here we do not have a comma, but it still returns the same information because by default, if we only have like one input over here, it refers to the constraint on the column instead of the rows. Another way that it returns the same information is by using the bracket, but we are actually specifying the name of it. So the second column is actually the gender column, and the first column is the ID column. So using this syntax, like these four and also I think a few more, you're actually getting the same results. So it depends on which one you remember or which one you like to use, but it in general gives you the same result. So this is DF2. What if we want to just to look at one single element in a cell? So for example, if we want to just look at, if we want to extract only the gender for the first observation, what we can do is pretty similar to before. We are still using this notation, but here we need to specify both the row and the column constraint because we only want this element. So the row constraint is that we only want the first row, and the column constraint is that we want the second column. So that gives you F, and that F refers to the cell over here. Yeah, and these two are just more examples on how to extracting rows and columns. I want to go over a slightly complicated example on subsetting the data frame. So here, we are using a really familiar syntax. So we have the bracket and then a comma separated. So we have a constraint before the comma, and then we have like an empty space after that. So based on the examples we went over before, because after the comma is empty, we have no constraint on the columns. And this line over here is actually the constraint on the rows. So let's take a look at what these are in specific. So this is the AND operator, meaning that we are using two constraints on the rows. The first constraint is we want the grade to be 7. So basically we want
any column.
So basically we want.
Oh.
Their question?
Sorry, I was speaking aloud, but I didn't realize I unmuted, and I was just speaking the logic. So any row or any cell within that column that has the value 70, correct?
Yeah, that's correct. And also the second constraint is any rows that has that the gender is male. So if we run this, the only row that satisfies both conditions are the second row because the grade is 70 and then the gender is a male. We have no constraint on the column, so we are actually returning all the columns over here. Yeah, so that's pretty much about subsetting a data frame. You can practice more just trying to specify more conditions on the rows and columns. So data frame is a two-dimensional structure. That's why you only have like two inputs over here. And the last type we're going to go over today is the table type. So table are built on list. And they are also a type of augmented list. So we talk about all the elements of all the columns of a data frame must have the same length. So because table is inherent from data frame, table also has the same requirement. All of the columns of the table also has to be the same. We can convert a table, we can actually take a look at this table example. So here we are defining a table with 2 columns, the X column from 1 to 5 and Y column from 5 to 1. So the type of tip is actually list because table is inherited from data frame and data frame is constructed on list. We can also look at the attributes. So from the class, from this line, we can see table actually inherits from data frame. And then the other ones are pretty similar to the attributes of a data frame. Those are the augmented vectors that are mostly used. So next, we're just gonna go over the import and export, and we're gonna finish that today by talking about how to get help in R. So for import and export, mostly we are working with CSV files. If you want to import, export, this example is from the Apple mobility data that I downloaded from the bootcamp materials. I believe it's under visualization or under modeling or statistics. You can just download it there, but it's also available on the GitHub page. So we usually just use the read CSV function in R. It reads a file in a table format and creates a data frame from it. So there are a few arguments for the read.csv function. For example, the header is the default is true, meaning that we're expecting the data frame to have column names. And the separator are comma because CSV is comma separated file. A more interactive way to import a data set is using this tab over here, the import data set. So we can choose from text. And then we can try to find where this data set is stored by going to data and Apple mobility data.csv. So here we can specify the name of the data frame we want to store in our environment. This is what the CSV file look like. Basically, it is separated by the comma meaning these two are different columns. So there's actually a lot of columns for this data set. And then we can specify the row names and separator. So separator is comma because this is a CSV file. And then this is what the data frame will look like if we import it in this way. So we have a few columns. And then if we put heading over yes, the first line will automatically be converted to the header instead of the first line. So this is how we import a data frame. We can also export the data frame using the package write_excel. So df2 is the data frame we just defined, and we can export it using df2.excel or df2.csv under the write_excel function. It will store the file under the current directory. Okay, so lastly, we just went over a few ways to get help with R, because I know today is just like really fast-paced. So there are a lot of questions you might encounter which are not covered today. So it's important that you know how to get help and how to keep learning R. So the first thing I would recommend when you work in R is to use the question mark to search for the functions, for example, the mean function or the t-test function or the t-test function. it will show the helper page for this function, like with this description, how to use it, and what its arguments are, what these arguments are expecting. And then it ends with a few examples of the t.test function. Also, we can use the helper page for operators. For example, if we want to search for what does this operator do, this is the assignment operator. We just need to put the quotation mark around it and then a question mark before it. Earlier, we got a question about the assignment operator and then the equality on the double equality notation. So this is the relational operators versus the assignment operator from before. We can also use this to check for packages. So there's a package called GLMNet, which is the a more generalized linear regression. So if you type 2 question mark and then GLMNet, it will bring you to the whole documentation on GLMNet. I won't go over to that in detail today, but you can just type in that in your R console and it will take you to the PDF version of that, what that package is. Another thing to try is just maybe Googling. So you just need to put R in the query and then your error message or the question you have. Usually there are a lot of answers. And I feel like Googling is pretty useful for trying to find the error message because sometimes the error message in R is not helpful. So Googling helps with it. And then the last one that I would recommend is to use Stack Overflow. You can first search for existing answers in Stack Overflow. So maybe someone else has the same question before and it's already got answered. So you can search for their answer and try to see if it works for you. If it's not work for you, you can also post your own question. So when you post a question, remember to add a few things in your question to make sure your code is reproducible for other people because they might want to try it on their own. So you should specify the package you are loading and also the data set that you are using. So I know sometimes we are working with private data set. So you sign some agreement and you cannot reveal the information within the data set to other people or other organizations. So in that case, you might want to try to make a dummy data set based on the structure of your data set, but without revealing any private information. So in that case, people can still help you and try to work on how to fix the issue without having access to your own data set. And then lastly, when you post a question on Stack Overflow or other platforms, make sure you uploaded your code to your question as well. Just make sure that your code is easy to read and you assign variable names carefully so that people can understand maybe what variables you are defining or what functions you're defining to use just to make sure to explain everything so that people can be more efficient when reading your code. I feel like these are all of the most of the resources you might want to use for getting help in R. We will go over more examples in R tomorrow. So I think that's it for today. If you have any questions, feel free to DM me on Slack or send me an email. I think that's it. Oh, also, I will briefly go over the schedule for tomorrow. Just a few seconds. Let's see. So for tomorrow, it will be Praxis to Power Day 2. We will meet from 10 to 11 a.m. Eastern time in the morning for introduction and logistics. And then from 11 a.m. to 12 a.m. Eastern time, we will have the alumni, SICSS founded alumni from 2022 for their roundtable on their research in progress. So here are the speakers for the roundtable. You can take a look at the slides and video and also the bio page for each of the speakers. And then after the roundtable, we will have a open office hour with organizers or SICSS-Howard Mathematica excluded content review or pre-revel material review from 12 to 2 p.m. Eastern time. So here are the pre-revel materials that you might want to go over if you have time. And then here are the SICSS and SICSS-Howard Mathematica planning team and a few videos if you want to take a look at it. There are more videos for changing the computational social science game and beyond. SICSS-Howard Mathematica throwback videos. So tomorrow at 2 to 5 p.m. Eastern time, we will have the second part of the R workshop where we will go over more examples. So it is 5:30. I will stop sharing and feel free to log back to the main room if you have questions from the net. If not, you are free to go. Or if you have any questions, feel free to email me or Slack me. Thank you.
Thank you all for watching. For more information on SICSS-Howard Mathematica, visit our website, follow us on social media, and join our email list.